Hi, good afternoon, everyone. Um, I hope you can all hear me okay. So today is parts 3 and 4 of my little lecture series about C++ for doing HPC or numerical computing, however you want to put it. So as ever, I'm very happy to take any questions as we go along. It's probably easiest if you type them in the chat window, which you should be able to see on Collaborate. You can also, there's a little button to raise your hand, which will make the Collaborate beep at me, so I definitely notice you. And yeah, well, thanks very much for joining me sitting on your computer on a beautiful sunny afternoon when you probably wish you were sitting in the park or something. Yeah, so before I get going, are there any sort of questions from the first half of this? So don't be shy to jump in with any from the last time as well in the first couple of slides as we get going. So so a recap. So one thing that a couple of people mentioned in passing was the iterators, just to go over it again a bit. So if we have some vector of data that we've got from some source, you know, you've got your standard C-style iteration over that, which is a fully explicit way of doing it. So you have to be aware that you have an index space that runs from 0 up to, but not including n. You explicitly deal with that. And, you know, obviously, after a bit of experience of programming, this is just totally transparent to you what it's trying to do. But you do have to be fully explicit about what's going on. In the middle is the sort of traditional C++ style of doing things, which hides some of the details. You don't have to deal with the explicit iteration. You can treat the iterator as a pointer to the current bit of data, but it's still quite verbose, even though the new auto type deduction does make it less onerous to type. And then at the bottom, you've got the newer range-based for loop that C++11 has introduced. And that hides a lot of the details from you while still giving performance exactly as good as the C-style iteration at the top. And a few more details about how templates work and the ways you might want to use them. So from the first part of 2 weeks ago, we had a very simple example with the sum template function that just adds 2 numbers of types that will be deduced at compile time. So we use this without specifying explicitly what type t was. So if we say x and y are both integers, and then we call the sum template function, passing those in, the compiler is doing what's called template argument deduction for us. And what this means is it examines the types of the expressions that you give as arguments to the function, and then it tries to choose t such that the type of the expressions given to it and the expected type from the function signature match, or at least are implicitly convertible to each other. And it's important to note that the template parameter t in this little example and the type of the function's arguments might be different, but you know, of course, they need to be related in some sense. So we've got f, g, and h here, 3 little trivial declarations here. So f, the type is just T. It is the instantiation type of the template. In G, we're taking a reference to that type. And in H, we are taking a constant reference to the type X. So they are not necessarily the same, but they are related to each other. And this will impact on how the compiler does the argument deduction, template argument deduction. So that means the deduction of the arguments of the types of the template. And this means that, for example, if you were to pass a const int to H, it would deduce T to be an integer, because that's implicitly convertible. As in, you can pass an int to the constant reference expression, that will be fine. So the full rules for doing this are pretty complex. There's a good summary of this in Meyer's book about C++. It's in the first chapter. It's actually free online, that one, so you can go and read this. And all the little intricacies are quite complex, but there is a reason for all of the complexities. But I find that usually you don't need to think about the rules explicitly, and just think about two things. First is whether you want to copy the argument or not, and whether you want to be able to whether you can handle a const argument. And if you want to copy the argument that is passed into your function, then you don't add the reference ampersand symbol to the signature. And if you do want to copy, then you leave it out. And for the constness, you want to try and be able to handle const arguments, because generally that gives the compiler more chances to optimize. It makes life easier for you in terms of reasoning about your code, but you will often need to be able to deal with non-const things. So in those cases, leave out the const. So the auto keyword is again something that people maybe are a little bit confused about. The auto keyword basically says to the compiler, you can deduce the type of this expression. And the auto keyword follows almost exactly the same rules as template argument deduction, but unfortunately is a bit easier to get wrong. So it's even more important to express what you want to do rather than just what's convenient to do. So basically, you can have three cases. So you can use auto X, and that will make a copy of the thing that you are assigning from, the expression you're assigning from. You can use a auto reference to X when you want a reference to the original thing, and you might modify it. And finally, you can use auto const reference to the variable when you want a reference to the original thing and you're not going to modify it. And generally, you want to try and use as low down that list as possible. So this is the sort of one of the big topics for what I want to talk about today, which is the standard algorithms library. And this includes around about 100 function templates that implement an algorithm. So these are things like count the elements that match some criteria, divide these elements based on some condition. And in the current versions of the standard, these all use iterators to specify the range of data that they're going to work on. So for example, if you want to use count, you might use a standard vectors begin and end iterators. So this little example here, so we want to count the number of zeros in some vector of integers. We call standard count using the full range of our data vector, and the thing we want to match against is there as the final third argument, and that is just the same type as the element, the value type of the standard vector. And that will just return the number of those for you. The second example I'm doing is using an unary functor to figure this out. So we define some little unary predicate is prime that examines its argument and returns a true or false flag, whether that's true or not. And then we call countif, and that will look at every item in the range and accumulate the total number of elements where the predicate is true. So here's a possible implementation of this template function. So it's a template with two template parameters, and its input iterator class and the unary predicate class, which could just be a function pointer. So for countif, the return type is some integer type. We give the first and the last elements in the range, and then we pass in our predicate function-like thing. We set the number of ones we found to 0. We loop through and all the ones until the first is equal to the last. Increment the first one. Then we call the predicate function on the value pointed to by the current iterator state. And if we get a true for that, we increment our count of elements. And then once we've looped through everything that's there, we return our current count. So I hope that shows that these are not super mysterious things that have to be very complicated. You can write very relatively simple implementations. So this little table is basically all of the standard library algorithms that I have used more than once. For each, which is just apply some function to every element in the range. Count and countif, so it returns the number of matches. Find and findif return pointer or iterators to the first element that matches, or the end if there isn't one. Copy and copyif, so it copies the input range to some destination if the predicate's true in the latter case. Transform is basically apply the function to some element range and store the answer in a destination. Swap, well, self-explanatory, swap two values. Sort, again, pretty self-explanatory. Sort the range in ascending order using the binary predicate that you provide, or if you don't provide one, it will use operator less than. Then lower bound and upper bound. So if you pass in a sorted range, so if you've built yourself a heap already, it will do a binary search within that to find a value matching some condition. Okay, so for each, so this is probably the simplest algorithm in some sense. So we just apply something to every element in our range. So the template is relative, the function signature is pretty simple. We pass in the first and last iterators and we apply some function to it. So why would you want to do this? And that is a reasonable question. So some arguments that you might, for why you might want to do this is you're clearly stating your intent to the other readers of your program. You can't get things like off by one errors or skip elements accidentally. It will interoperate well with other range-based algorithms, and by a range I mean a sort of a first and last iterator pair. And if you already have your operation written in a function, it's very concise. But I would personally, I think that a range-based for loop is usually the right option instead of a for each. So yeah, there are now 4 ways to iterate through some range of say, a standard vector here that I've talked about today and 2 weeks ago. So there were 3 we've talked about already, and then the last one you've got the new standard for each. So transform is another one. This is a very powerful function, and it's basically the equivalent of the sort of map concept if you're a functional programmer. So what you do is you pass in the range of your inputs and pass an output iterator that points to the destination's starting point, and then you have some unary operation, transformation operation that you want to apply to every element in the input range and store in the output. So a little example, if we transform some data from beginning to end, and then we're actually going to store this back into its input destination. So we're calling this double in place functor that I meant was on the previous slide also. So for the rest of that table, I suggest just having a little look at the documentations online. The cppreference.com is very thorough. But why might you want to do this? So the implementations have been written by someone else, and if they're in your compiler's standard library, you can be pretty confident that they've been well tested by the suppliers of your system. So there's some work you don't have to do, which is always great as a software engineer. And the library might be doing some platform-specific optimizations that, while you could implement, you probably don't want to maintain them across multiple platforms. Hello, Jose. Yes. Don't worry. We're going to talk about lambdas. That's coming up. Don't worry. So the one reason is that I find them useful is that they form a language to communicate with other people. And this isn't just other people, it also includes yourself in the future. And they express the intent of what you want to do, which is obviously an important thing. So what's going on in that first code fragment has to be read in detail. Whereas the second example, is a bit easier to understand at a glance what's going on. It's copying from the images thing into the cat pics thing if it contains cat, and you can read this much more quickly than the first one. There you go, Jose. So all of these algorithms that I've just talked about, they need you to provide a function or a function-like object as an argument, which is going to actually implement the behavior that they need. So having to declare a new function for one-off use in an algorithm call is quite inconvenient. It moves the code away from its use site, which is confusing and adds the maintenance burdens. And worse, you might even need to create a custom functor object every time that's going to have its own members, and you've got to think about how you're going to construct this and so on. So for example, if we wanted to square some input number and add a constant to it, so we want to do z squared plus c, for example, if we wanted to implement that in a sort of well parameterized way, we might end up writing some functor type class here, square and add const functor, that's going to have a member variable, the constant. It's going to need a constructor, wherein you tell it that constant, and it's going to need an operator parentheses, which is the function call operator overload in C++. And this needs to accept one argument and give back another one. And then we actually encode some meaningful information there in that line. And then where we use it, we need to say, if we're going to go store our answer in some vector and accept some input vector as well as the constant, we need to construct it and pass it into transform and then return the answer after that's run. So C++11 has introduced a concept to C++ of a lambda function, also known as a closure or an anonymous function. And this is a function-like thing that does not have a name, like the functions we've always used in C and C++ so far. You can define one wherever you like inside a function or not, and you can bind them to a variable and call them and pass them around just like any other value. The newer thing for C++ is that they can capture local variables, either by value or by reference. And we'll talk about what capture means in a moment. One sort of proviso is that they have a unique unknown type that you can't get at unless you are a compiler writer. So you have to use auto if you want to store them in a variable, or you could also pass them straight to a template argument and let the compiler deduce the type to whatever it is when it instantiates the template for you. So we can make our example less verbose. So we don't need to define a functor class outside of our little function. We just define our lambda here. So this is what the syntax looked like. We put in square brackets the list of the captures. So here we're just capturing C, our constant. We're giving the function argument list there, and then the function body, just as a normal function body, it's just z squared plus the constant. And then, of course, because it's a statement, we do have to terminate it with a semicolon. People sometimes get a bit confused by that, but this bit creates the lambda, and then we assign it, and that's our statement done. And then we can pass this function straight into our standard transform here. And of course, we can make it a little bit less verbose again by just defining the lambda in place and passing it without binding it to a name. Oh, have I missed a close parentheses? I have. Sorry, just jotting that down so I can fix that. Right, so this is the sort of specification of what a lambda looks like. So the square brackets, here is the new syntax that sort of introduces the lambda and indicates that what follows is indeed a lambda expression. So then we've got a function argument list, which is exactly as you're used to creating for your own function declarations. Then the function body is, again, exactly as you're used to. That's just the normal function body, so 0 or more statements like you might have in any function. There's no restrictions on what you can put inside it in terms of the usual constructs. Anything you can stick inside a normal function, you can put there. So this arrow return type here is the new C++ style syntax for specifying the return type of a function. You can, in fact, do this for any function that you declare, as long as you put auto first as the return type. This basically just is a placeholder indicating it's indeed a function, and then the return type will be specified later. But you have to put it afterwards for a lambda. This tells the compiler what type is going to be returned, but you can skip it if the return type is void or the function body is only a single return statement, at least in the C++11. When you move to C++17, you can let the compiler deduce it for you based on the return statement inside your function body. And then finally, we'll go back to the first thing, the captures. So this is a list of the captures that are made by the Lambda. So you can capture a value by copy. So you can just put its name there. So if you have a local variable called local, you just write its name there, and its value will be stored by copy inside the Lambda that is produced by this statement. Or you can capture it by reference. So if you just put an ampersand before its name, it will be captured as if it was a reference member of a struct or something inside the function body. So this does create a function object of a unique unnamed type. Oh, Jose is asking a question. So what's the difference between passing an argument in the arg list and capturing it in the square bracket? So what's the difference between putting a value in the arg list and in the capture list? So this creates an object executing the Lambda statement. And this object has two ways of getting data when it runs its function body. It can either get the data from what was captured when it was created, or the values that are passed in when it is run. So, for example, if you capture things when you create it and then return this from a function, you are keeping the variable, the values that were present when it was created, not when you call it later, which could be at any future point in your program if you hold on to it. Does that make sense? It's the difference between, for example, the arguments you pass to a class's constructor, which are stored inside it somehow, and the values that you pass to it when you call its member functions. Does that make sense? Okay. Okay, so yeah, like I said before, this creates a unique type that you can't get at the name of. So if you want to store the Lambda that is created, you have to use auto to declare the variable. And then you can call it the Lambda like you would any object that has an overload of operator parentheses, the function call over operator. So for example, if we go back to the squaring and add a constant one here, and if we were to create it with our constant, whatever C is, and then call it with the argument 3, we would print the value of 9, 3 squared, plus whatever the constant was. Okay, and it's also important to note that because it doesn't have a name of its own, it can't take part in any overload resolution. So you can't, for example, go auto some function name that's got a load of overloads already equals a Lambda and have the Lambda take part, because the function itself does not have a name. You have just bound it to a variable with the same name, if that makes sense. Okay, so a very, very brief quiz. What does this following set of line noise do? Could anyone take a guess? Dennis says a no-op. Yes, that's correct. So what this is doing is this is introducing a Lambda that captures nothing. It takes no arguments. It has no state no statements, and then we're calling it. So it is indeed a complete nothing. Okay, so again, why do you want to? So using it with the standard algorithms library or any other library that you might want to write that needs to be given some functions to do its work. So they're great for passing in sort of little one-off pieces of code. So for example, if you need to sort some list of molecules and you want to sort them by their charge member, you can quite easily create one in line that just takes two molecules and compares the charges with operator less. And you're done. The library will take care of doing the sort for you. Another very useful place where you might want to use them is if you want to do some very complex initialization on something that you would normally want to be const. So for example, if you need a set of random numbers of some size, and you're never going to modify this during the rest of your function, you may want to mark it const, but in the usual way of doing things, you can't. However, here we can create our lambda that captures the size. It doesn't take any other arguments when we call it, and it returns a standard vector of floats. Then inside we initialize the answer to the right size. We call some random number generator to generate each element. And then we return the standard vector back to the call site, and then we call it immediately. So note that there are the parentheses there to actually call it. And this will do the, so this thing will only be mutable while we want to be modifying it. And from then on after, it is constant and immutable, which is useful in terms of reasoning about what's going on. So a few rules of thumb. The most important thing is to be careful what you capture. Okay, if your lambda is being used locally, so that means that your lambda is going to exist only in the local scope of your function and any functions that might be called by it. So that includes passing it into algorithms or other things. You're probably going to want to capture things by reference. And this ensures that there's no copies made of any data. And if you want to be changing things, which you have to specify explicitly with the mutable keywords that you can read about in the docs online, this means that you're not doing extra copies. You can change things as you need. But if you are using the lambda elsewhere in your code, really, especially if you return it from your current function or you're assigning it into some other object that's going to outlive your local scope, you probably want to be capturing by value. So remember, references to locals, any local variables you've got, are invalid after the function has returned. So your lambda might be holding on to a reference to something that has been destroyed. And that could cause undefined behavior, most likely either garbage results or a segmentation fault. So even if they are still valid, it's much harder to keep track of what's going on in your program. So that's generally something you don't want to do. And the last one is possibly a bit more controversial and more just what I think, is try and keep your lambdas short. Anything more than, say, 10 lines, you should probably be moving it into its own function with a name and a short documentation string, if it's more complex, into a little function-like object. Sorry, excuse me. Okay, so traits. So I'll sort of explain what these mean as we go through. So type traits are a very important generic programming technique that's used across the whole of the standard library in C++. It's basically a sort of if, then, else, or perhaps more accurately as a sort of a switch case type statement but instead of acting on variables, it's acting on types themselves. So what you generally do is you provide a template class that has either type defs or member functions that specify the configurable parts of your algorithm. And then your generic algorithm uses this class specialized on the type that it's currently working on to select the behavior that's going to happen. And the advantage of this is you don't have to change the source code of either your algorithm or the type that you're working on to be able to configure things to adapt to each other. So the standard template library has a couple of header files that contain traits. The type traits one has lots of these trait classes for handling, for querying the properties of types. For example, the standard isPointer class template accepts one type, which is the type that you want to query, and inside it has a type def value that will either be true or false depending on whether the type you pass in is a pointer. So, for example, int would give you false, but if you passed in int star, that would give you true. And there's a large number of these for querying many different aspects of what a type is. Another one is the numeric limits template class. So if you pass in one of the built-in number types like float, double, int, char, and so on, this will give you a lot of parameters for these, such as the smallest and largest values, whether they're integers, floating, float min, float max, the exponents available, and so on. You also get the infinities for the floating types. And there are an awful lot of traits that are used behind the scenes everywhere in the standard library for efficiency. So there are things like the traits of iterators that describe whether they can go backwards and forwards or random access and so on. So just to motivate a little bit, I'll give you a real example from a project that I've worked on in the past. So if you want a sort of C++ style wrapper around the message passing library, does anyone not know what MPI is here? Okay, I'm going to assume you know what MPI is, at least roughly. So when you make an MPI call, you always have to specify the types of the data that you want it to transfer, whether it's an MPI float or an MPI int or whatever that is. But you might take the opinion that since the compiler knows these types already, you should not have to be specifying this. So you may want to have an interface that looks like this. So you have some communicator class that you whatever, and this has a template function that's going to accept a vector of a standard vector of some data that it's not going to modify, and you just want to say send it to this destination rank and give it this tag, and you want to be able to use it something like this. You get your communicator from somewhere, say it's MPI comworld from whatever the interface looks like. You create some data, and you just want to go send the data to whatever other rank it is, okay? And have the library know the type and the size of your vector. Since it's got all this already, why should you have to re-specify it? So you might have your very simple implementation look like this. So you've got your communicator send member function. It takes the data, the destination, and the tag, and you call MPI send. You cast the data to a void pointer. You pass in the size. That's nice and easy. You've got to put something for the data type. So the question is, how do you fill in that data type here? So for all the types in the MPI standard, you could provide a specialization for each of them. So you could do a template specialization, or for integer here, say, where you just explicitly put in MPI int, and so on for double and char and float and all the rest of it. So the problem is that there are quite a lot of types in the MPI standard. I think it's about 20 offhand. And there are a lot of MPI calls, about 200, that you may want to wrap all of them if you are writing a full-featured library. And so you've got to write m times n 4,000 odd specializations, which is horrendous. And then you've got to think about how you're going to add any custom types that your user is using, because MPI does support custom data types. So the user would have to be able to mess around with our little MPI library here, which is not a good thing. So the traits-based solution is to create a class that tells our functions how to handle these different types. So, for example, we would create a struct data type traits, or maybe MPI data type traits would have been a better name. And we provide one member function, which is the function to get an MPI data type that's suitable for this specialization. And we don't provide a default implementation of this. So this means in the generic case, we don't know how to do this. And so if we were to not provide any more, this would never work, but we'll come back to that. So inside the implementation of the send function, we specialize the traits class on our current working class, and we call the get static member function, and that will return the MPI data type we need to make this work. And what we've got to do is provide these specialized definitions for all the types that we know how to handle. So we could specialize this for an integer and a float and so on for all the other types we know about in the standard, and any in our application we could specialize it for whatever special types. For example, if we go back to molecular dynamics and we've got a molecule type, we could specialize it for that, and that could we just have to make sure that our application has committed the data type to MPI at some point before. And then if we try to call this send member function on the data type that we haven't specialized for, we'll get a compile time error saying that there's no existing specialization for this. And so it will be flagged at compile time that we haven't done this, which is quite efficient. Why isn't this going to the next one? Oh, and yeah, so there's plenty of documentation and examples of how to do this online. Just a quick Google for C++ type traits will throw up lots of examples of people using this. So that's it for part one. I'm very happy to take your questions about anything I've talked about now or last time, or if you've had a look at the exercises which are on GitHub. I'm happy to talk about that for the next 20 minutes or so. But thanks very much for your attention. Questions? Hello. Harvey asks if I can differentiate a functor from a function. So a function in C++ is, well, what you think it is. It is a piece of code for which you've written a function declaration and then provided a definition. Whereas a functor is an object which has an overload for operator parentheses, which I'll just, so you've got your, it's any struct for which you've defined an overload for operator whatever, and then whatever args it takes, and a body, if that makes sense. Okay, if no one has any further questions, I'm going to sign off. There's a seminar happening here in EPCC, so I'm going to restart at 4:05 instead of at 4 sharp. Yeah, so I hope to see some of you then. We're going to be talking about sort of frameworks for portable performance across multiple architectures. Then, right. Thanks, and talk to you soon.